Good afternoon, everybody. And again, my camera has decided to be a jerk. I don't know why it does this, because before I start the stream, it looks just fine. So let me just 1934 1087. Let's just remove it. And let's add video capture device. And we'll make it my camera. And there we go again. I don't know why it's doing that. I don't know why it's decided to be a jerk, but a jerk it is. But we got it fixed, and that's all that matters. I should look and see, because what I really want to do is at some point capture the size of this. You can't see it, but when I'm looking at it in OBS, I want to make sure that's always the same size, because if this keeps happening, I need to write down what it is. And it's not pausing during the stream, it's just acting strangely. Oh well, maybe I need to update it. Maybe I need to shut down, start it up again. Who knows? Let's see if there are any updates. There is a new update, so hotfix changes, bug fixes. Is there a bug fix in here about that your camera freezes? I don't know. Maybe there would be. So who knows? But hey, we're okay. All right, let's get the music going and make sure I'm at a good volume for that. And there we go. All right. So in the last stream, I think I was getting close to the answer, but it seemed like I was like 1 or maybe 2 off, which is kind of bizarre. But right before, as the introduction song thing was ticking down, I kind of thought about it, and I'm like, why would we be missing this one here? Like, why are we missing this answer? And I think I realized why, or at least part of the reason why. It's because when we're looking past our current position, like here, we only consider, is it path? It could be the end. And in this case, the cheat, that's exactly what it could be. So I think what we need to do is say var second position is equal to, or second character. And if that, if that is equal to this, or that is equal to end, that's what, I don't think this solves everything, but I think this is definitely a I definitely think that's the answer we are looking for. Okay. Okay, so now we got to do it on all those. So let's get that. And let's say it's either got to be the path, or that's got to be that. South, I'm going to do west. By the way, I've been looking for potentially getting a new keyboard. I like my keyboard. I like using the Sculpt. That's the one I have. I have that both for my personal use, and then also I use it for my workday stuff. But while I like the ergonomic keyboard, I also do like the clackety-clack of mechanical keyboards. But typically those have always been straight, and I don't like that. So I want to get one that has the ergonomic shape. And I found a couple. I've gotten a couple of recommendations. I just have to now go through and say, you know, which one should I bank on? So that's that. And then let's do the north one. And then I'll check my work real quick. And we'll see if it makes any kind of difference. Okay, so let's go back up here. We'll basically just grab that. We said it's either path or end. Grab that. Path or end. Path or end. Okay, so now let's see if that helps out at all. And it does. I still got the feeling one of these is going to fail, but let's see. Yeah, one of them still fails. That's better though, but we're missing one. And why are we missing one? Which one are we missing? So when we do 4 and 30, which is interesting because the 2-1 works. Like if I do that, that works. So it's like one is just off. One that gives you a savings of 4, there should be 30 of them, and we are saying that there are... Yeah, I know one. I wish... I hope that gets updated. Be nice to see like the list and stuff coming here. So right now... Damn it. Okay, so 430 is giving 29, not 30. But 244 is giving the correct answer. Correct, not correct. Correct answer. I was like looking at the word, I'm like, okay, 44. I'm curious. What happens if we set a savings of 3? They still all fail. So a solution of 4 is missing just 1, and it's falling down to the 2 case here. That's interesting. That's going to be really hard to find. Because it's a sneaky one. What happens if we run it? Yeah, we definitely get more. I think yesterday I saw like 600 something. Now we're getting 1411. Although, did we change the answer on that? No, we said 100. And that's what it's supposed to be. Save you at least 100. Although I got the feeling if I submit that, that would be a wrong answer. So we got to figure out why. When you do a savings of 4, we should be getting 14. Well, we should be getting 14 more than this one. And we're not. We're getting 29. We're missing 1. Just 1. And it ends up not being a 3, because if we change this to a 3, it doesn't work. It's actually too much. If we make it a 4, it's too little. That's interesting. Set of my foot wrong. But when we get to 2, it picks them all up right. So there's something about there's something about 5. What happens when we say 5? It's still 16, so it doesn't jump up until 4, but it doesn't jump up enough. You go to 3, and it jumps up twice. And then 2 gets the rest of them. So these small cases, there's something odd about them that I'm not picking up correctly. And if we look at a 4 case, for example, that would be something like you're here, and then you cheat over to here. And, well, we do know that a 3 case is going up by 2, and it's missed at 4. So we could look and see, when you tell us that you think the savings is 3, let's look at those indices. So we want to say savings is equal to 3. And that should happen twice. There's 1. And there's 2. And there's 3. Oh, it's all the ones that are 2s as well. This seems to work, kinda, when the value is big enough, but when you get small enough, something is not working out correctly. So let's just look at this. A start position of x1 and 2. x1, 2, x2, 2, x3. That's wrong. Wait, x is 1, y is 2. Oh, I'm sorry. That's correct. I was off by that. I was going the other way. But it says that is a cheat. But it's saying the starting index is 0. Which is interesting. We think we start at the... Well, that we do because it goes 0. Wait, why are we getting screwed up like this? We're saying... Okay, we're getting into it. We're saying we start here, but then we're saying y3 here, and then we say y1, and then we say 2, 1. Three, 1, 3, 2, 3, 3, 4, 3, 5, 3, 5, 2. So at the beginning, it gets a tiny bit messed up. So why at the beginning? Oh, I know why. But that shouldn't. Oh. That's why it's getting screwed up a little bit, I think. And then eventually it, with some of these beginning ones, it matters. And then some small, I guess maybe that's it. Okay, but I think I know what's going on here is that, and this is something that's interesting, is we don't care about the entire path, even though arguably this is the first picosecond you consume. But this is the start. And so I'm wondering if we go into our solution and we say our path let's move these down here because we want to get our start position in. Now what happens when we do all of our test cases? They all succeed. So what happens when we get to 3/30? That should still be 30, right? Yep. And only when you go to 2 does it jump up. That was the problem, is that we weren't considering that one. So now what happens when we do this? I think it was the same answer. I'm not sure. Is that the right answer? Ding, 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 ding. And there was much rejoicing. Yay. Okay, cool. So we got that one done. Git commit. Part 1 of day 20 is complete. Not too bad. Hung me up for a little bit. Got me a little bit confused, but it wasn't terrible. I think the in the what was I trying to say here? It messed me up a little bit. Not as bad as some, like the one with the computer and trying to print out 16 different numbers or whatever. That one I've got to come back to with part 2. But this one, a couple bugs here and there, but nothing bad, and I was able to eventually figure out why. So not too harsh. But as we know, part 2 is always harder. The program, I'm going to pause the music while I read this, and I'll put it back on, for my edification, if anything. The program seemed perplexed by your list of cheats. Apparently, the 2 picosecond cheating rule was deprecated several milliseconds ago. The latest version of the cheating rule permits a single cheat that instead lasts at most 20 picoseconds. Now, in addition to all the cheats that were possible in just 2 picoseconds, many more cheats are possible. This 6 picosecond cheat saves 76 picoseconds. At most 20 picoseconds. Because this cheat has the same start and end position as the one above. It's the same cheat. Even though the path taken during the cheat is different. Yes, because you're basically saying, and you got to be a little careful again with wrapping around the map. You're basically saying if the first thing, you don't even have to care if it's a wall anymore. You can just say, in this direction, am I at least, well, no, that actually gets to be more messy because it can be 20. So now you can have 20 branches going off from one point, and you could have one that goes 20 here, you could have one that goes 20 here, 20, 20. You basically have a kind of circle end target, so to speak. because this cheat is it's the same cheat. Cheats don't need to use all 20 picoseconds. Cheats can last any amount of time up to and including 20, but can still only end when the program's on the normal track. Any cheat time not used is lost. It can't be saved for another cheat later. You still need a list of the best cheats, but now there are even more to choose between. Here are the quantities of cheats in this example that save 50 picoseconds or more. Yeah, and you could just go right from the start to the end and cheat that way. But yeah, this one's tough because, again, if you do this hard-coded or brute force, I can see where this will take quite a long time to finish. Because you could almost think of it as, here's your starting point, or wherever you are in the maze. Like if you were here, for example, and you can't go out, but if you went this way, there's basically a 20-second kind of circle around here that lets you cheat and get all the way to the end. But there's still also the cheats that let you end up like right here. You could go from here. No, I don't want Copilot. Jesus. You can go from here all the way down to here, for example. Well, the other way. You could go from here all the way up to here. You could go from here all the way over here. That's a cheat. And so there are lots of cheats. Many cheats of many different sizes at every different point. And that can get to be ungodly huge if we're not smart about it. Because this cheat is the same. Yeah, I'm starting to rethink my strategy of trying to do part 1 and part 2. Part 1s are usually not that hard. And usually, not always, but usually. And I have 21, 22, 23, 24, and 25. I've got 5 left. What I've also noticed, and not always, but what I've also noticed is that sometimes leaving a problem just sit in my brain will a couple days later afford itself to letting it be solved. You know, so maybe what I should do with these last problems is just say, you know what? Let's just let my brain ruminate on it, because I can kind of see in my head what you need to do. The problem is, you got to be really smart in terms of not getting into an explosion of possibilities. You know what I mean? I almost wonder, I was going to say if you could start from the end and go out, because that would give you that 20 picosecond radius, sort of, if you want to think of it that way. But it's any point. And again, the main data set is far bigger than 20. You know, we're looking at something like this. And I don't know, like for example here, how that works. That's a line, that's 18, so that's a bad example. But let's say here's 22, and there's 88, 142. So somewhere like in here, if you see where my thing is circling, that's a whole bunch of cheats that I could try just at that one point. And some may end up going backwards and some go forward, whatever. I can't tell just by looking at this which direction everything is going. But the problem is that you have to do that every single point. So how do you do this without making this just completely fall over with possibilities? So my brain is telling me, let this simmer, let it cook, So that's what I'm going to do. I'm going to let part 2 of 20, and I am going to say it explicitly. Do not give me any hints. Do not give me any suggestions. Do not give me even a little bit of a, did you think about this? Okay. Because I'm not saying I'm lost. I'm just saying I need to let my brain stir on this for a little bit. Okay. So we're going to go back to the calendar. So you can see now I'm going to skip 20, but we're going to go right to 21. And what's funny is that when you do Advent of Code, if you do it like what I did in 2022, which is every day I solved a problem. I think there was maybe one that I had to hold off on and come back to. I think, I'm not sure. But I think with that calendar, I was very dogmatic about saying I'm not going to move ahead on a day. And I was able to pretty much keep up with every day except maybe one. And then I got back on track. So when you wait this long, all 25 days are available. So I'm kind of just thinking, let's move on. Let's see what's available on 21. Okay. So we will come back to it eventually. Okay, 21. As you teleport onto Santa's reindeer-class starship, the Historians begin to panic. Someone from their search party is missing. A quick life form scan by the ship's computer reveals that when the missing Historian teleported, he arrived in another part of the ship. The door to that area is locked, but the computer can't open it. It can only be opened by physically typing the door codes, your puzzle input. Hold on, I got a message. Okay. But the computer can't open it. It can only be opened by physically typing the door codes, your puzzle input, on the numeric keypad on the door. The numeric keypad has 4 rows of buttons, 7, 8, 9, 4, 5, 6, 1, 2, 3, and finally an empty gap followed by a 0 and an A. Visually, they are arranged like this. If you've ever seen security to type in keys, numbers, this is very familiar. Unfortunately, the area outside the door is currently depressurized and no way can go near the door. A robot needs to be set instead. The robot has no problem navigating the ship and finding a numeric keypad, but it's not designed for button pushing. It can't be told to push a specific button directly. Instead, it has a robotic arm that can be controlled remotely via a directional keypad. A directional keypad has 2 rows of buttons, a gap, up, A, activate on the first row, and left, down, right. Visually, it's arranged like this. When the robot arrives at the numeric keypad, its robotic arm is pointed at the A button in the bottom right corner. After that, this directional keypad remote control must be used to maneuver the robotic arm. The up, down, left, right buttons cause it to move its arm 1 button in that direction, and the A button causes the robot to briefly move forward. Oh, press it. So when it says forward, it didn't mean a direction. It meant if just pressing the button. For example, to make the robot type 29 on the numeric keypad, one sequence of inputs on the directional keypad you could use is, move it left to 0. Move it up. Oh, you got to press, right, you want to press 0. A to push and then up A to push the 2 button, right up A to push the 9 button, and then down A to move the A to the A button and push it. In total, there are 3 shortest possible sequences of button presses on this directional keypad that would cause the robot to type this, that, and that. Unfortunately, the area containing this directional keypad remote control is currently experiencing high levels of radiation and no one can go near it. A robot needs to be sent instead. When the robot arrives at the directional keypad, its robot arm is pointed at the A button in the upper right corner. After that, a second different directional keypad remote control is used to control this robot, except that one is typing on a directional keypad instead of a numeric keypad. There are multiple shortest possible sequences of directional keypad button presses that would cause this robot to tell the first robot to type that on the door. That sequence is that. Unfortunately, the area containing the second directional Jesus, what is it going to be, like 500 of these for the part 2? Is currently minus 40 degrees. Another robot will be needed to send on that keyboard. There are many shortest possible sequences of directional keypad button presses that would eventually cause this robot to tell the second robot to tell the first robot to eventually type that. One such sequence is blah, blah. Unfortunately, the area containing this third directional keypad remote control is currently full of historians, so no robots can find a clear path there. Instead, you will have to type this sequence yourself. Were you to choose a sequence of button presses, here are all of the buttons that would be pressed on your directional keypad, the two robots' directional keypads, and the numeric keypad. In summary, there are the following keypads. One directional keypad that tells that you are using, two directional keypads that the robots are using, those and those, one numeric keypad on a door that a robot is using. It is important to remember that these robots are not designed for button pushing. In particular, if a robot arm is ever aimed at a gap where no button is present on the keypad, even for an instant, the robot will panic unrecoverably, so don't do that. All robots will initially aim at the keypad's A key, wherever it is. To unlock the door, 5 codes will need to be typed on its numeric keypad, for example, these numbers. For each of these, here is a shortest sequence of button presses you could type to cause the desired code to be typed on the numeric keypad. The historians are getting nervous. The ship's computer doesn't remember whether the missing historian is trapped in the area containing a giant electromagnet or molten lava. You'll need to make sure that for each of the 5 codes, you find the shortest sequence of button presses necessary. The complexity of a single line is equal to the result of multiplying these two values. A single code, the length of the shortest sequence, the numeric part of the code, the above example, find the fewest number of button presses you'll need to perform in order to cause the robot in front of the door to type each code. What is the sum of the complexities of the 5 codes on your list? Oh, that's cute. For some version of cute. It's also interesting that the input here is basically the same that we have here. Now, let's save as. Again, I'm sure there's one cute trick to doing this. So to do this, what you want to do is basically find the shortest sequence. And it doesn't matter if it's one of, like they said, there's 3 of these, right? Yeah, these. It doesn't necessarily matter. Well, yes and no. Because is it possible that if you can keep a robot going in the same direction, Like if you look at the first number here, 319. Now, if we saw that as a human being, and we were here, we would go up 1, 3. We would not go all the way around like that. We would just go left, left, press 1. To get to 9, we could go up, over, right? But it's less costly to go up, over. But here's also another thing to think of. If I go 3, 1, 3, 2, 1, and I'm here, that means that I'm currently on. I was doing. Well, so I was on A. So if I tell it to move up, it moves up. Now I hit A to activate it, so it's A. To get over to 1, the quickest path would be to go left. But to go left, I have to tell this robot here. Like I could just press the left button there, but there is another robot that is controlling this. So now it needs to tell it to go down, over, activate, which will get it to 2. So it needed to hit this arrow. Then it's got to go over, up to hit activate. I'm sorry. No. We were in A. We want to go up to 3. So we need to tell the series of robots here. We need to tell this one to go over and hit A so that it tells it to go up and hit 3. So now we're still on A. Now we need to tell it to go left. To tell it to go left, we needed to tell it to go 1 down, 1, 2 over. So it goes to 2. Over again, it goes to 1, 2 to the right, and up to say 1. Now we want to go to 9. We could tell it to move over, go up, go down and over, go over, hit A to activate it. Okay. Now we got to go to the end. So we want to go over, down. Now we'd have to have something say A. So, wow, this is... I mean, it makes sense. You need to have one robot tell another robot, tell another robot to tell another robot. Is that how many there are here? I'm curious. What are the stats on this? Yeah, this is the one that had the least amount of people doing it, finishing it. Although it did have 18,000, so I could see where this would throw people because it is a little. And I'm wondering is if like I was on this first robot and I could be there. Excuse me. So if I had to type this on here, I'd have to say, move it to 0, move up. Oh, I'm sorry. You're trying to type in 029A. So we move it to the left, hit A. Then we need to move it up an A. Then to the right, up an A, and then down A. And you'll notice here that this route, I would argue, is worse than either one of these routes. Okay. Because this one would require you to go up, down, over, hit, over, back up, hit. This one just would require you to get to that, press it, that, press it. Man, I might skip this one because not only do you have to optimize, you know, this is what hits it. If I had this one, what is, you know, not just the best one to control the sequence to hit the numeric entry here, but then what about the one hitting it and the one hitting it? You can see down here, it's like, that's what we want to do. So we want to have like the robot doing that, but then we have to have this robot doing this to get this to hit, to get this to hit. And then we need this robot to control this robot to get that sequence, to get this sequence, to get this. And so I'm kind of wondering, looking at the input, let's close this, 21. They all need to get back to A, and they all start at A. Okay. And so I'm wondering if you did something like, if I need to get from A to 3, what is the best way to get to it, assuming I'm starting on A? And you can always assume you're starting on A because that's where you have to get back to, because you have to do that to press it. You start at A on this thing, and we're starting at A on this thing. Okay. And so we need to tell it to get up, because that's its initial position, is it's pointing at A. We're never going to start, none of the sequences actually start with an A. And so we could say, well, what's the best way to get to 3, assuming we're at A here? Okay. And so to do that, the best way to get from A to 3 here would be to go up and then go to A. Right? That would be the shortest path. You could do something like go down, go over, hit this, which gets you to 0, come over, go up to 2, come down, go over here, go to the right to hit to 3, and then go up to hit A. But that's not optimal. Nowhere near close to being optimal. Right? And so you could have something that says, for every number here, what is the best way to get to it? Assuming you're starting on A here. And just keep a table. And say that chunk is what gets you the quickest to get from like 7 to 6. Because 7 to 6, if I could physically just pick up my finger, I could go down over, and then hit A. But that's not optimal because I'm starting at A. What I could do is I don't want to go over, down, up, hit A. And then go down, hit A, down. I'm sorry. No, you wouldn't do that. I'm sorry. You're here, but to get down, you have to go over, down. And then from 4 to 5 to 6, you'd have to move over, press A because you got to. But yeah, now you have another robot controlling that robot to tell it to do that, and then you need another robot to get to that robot. So how optimal are all these paths? Maybe I skipped this one because I'm almost wondering if I'm getting to the point where it's just not optimal to do these on streams anymore. I don't know. If you look at the stats on the board here, and again, part of this too is just people's enthusiasm. I think you get people that start out that are really enthusiastic, and the first couple are not too hard. Okay, but as you get farther along, in part, some of them do get harder, but also they do get, you just get people to fall off and go, yeah, I'm just bored, or I got other things to do, or I just can't put in all the time to do it. And so you do see that kind of curve, kind of where I'm getting with this. Like I could see 7 to 6. If I had to do it here and I was on 7 and I need to move it over to 6, I would say, well, just, you could go down, you could go over, and then press A. Okay. I could also just say go over, go down, and press A. Which one gets you the better route? If I'm on A and I'm on 7, I would need to, go over, go down, press A, because that presses the down here. Then I would need to move over, press A. Then I need to move up and press A, because that gets me over to 6. Another way to do this is just to go over, and down. So I could go over, press A, because now that will, actually, no, I'm sorry. I'm getting confused as to which level I'm at. Let's just take some notes here. So that's 21. Right. This is just saying if I was at the robot that was controlling the robot to move, to do 0, that, this then this presses A, then this presses 2, then this presses 9, and then this presses A. And so for all of these, there's 11. How many paths would you have to figure out what's optimal? Right? Like if I'm on A and I had to go 0, the best way would be to say, well, you got to hit this and then hit this. Right? But yeah, it feels like it's an optimization problem, but it keeps, like, what's optimal here and then what's optimal in the first robot. Like they said, this one, all three of these have a corresponding, well, if I want to go from here to A, I need to have another robot that I need to tell it to, you know, to move down, then to move over, hit A. Yeah, like you're seeing here, move down, move over, hit A. That would then tell this to hit, tell it to go move down, move over. It would now hit this one here. But which one of these three has a shorter sequence above? And then for that one, which one has the shortest sequence for above? And so for your sequence that you need to generate here, for each number, what's the shortest sequence down here? But then what's the shortest sequence here? I don't know. Nothing's quite coming to mind that I feel like is a strong way of implementing this. I fear saying what's the shortest way to do it here, knowing that I have to have something above it to tell it to get to there. Because it's not just the shortest sequence like they're saying here to do 0 to 9A. It's also, well, what would, I keep repeating myself, but what would be the best solution given that we have three solutions that could do that? Well, how many possible paths can you get to do to tell it to do like this or this? You always know that when you're at a number, you're starting at A here. You have to be. So eventually, when you get to whenever you're at a number, and you need to get to another number, all of the robots are at A. They have to be. Because they all told, this one told it to press down, which would have told that one to press A, which would have told that one to press A, which would have told that one to press down and press like 7. Okay. So it's not when one robot hits A that they're all there, but once you get all the robots so that this one on this keypad is on the number you want, then all 3 have to be on A to get it to press that. And so you could say, well, like if I'm on 7 and I need to get to 8 here, and if I'm on A here, what would be the best way to do it? I would say move down. But to move down, I've got to get this one from here to here. And then to get the other one there, I've got to have it do the same thing, go there and go down, right? What's interesting is that if you take this at gospel, it's giving you, like, for 0 to 2, it's telling you what the fastest path is there to get. Now, this is not going to help out for everything. And I'm not saying this is the sequence. I'm just saying there is some section of code here that's saying that gets you from 0 to 2. And it would have to end on an A. So we'll just say it's this. I really don't know. Okay. But then, like, you need to move to 2 or from 2 to 9. Well, then there's going to be some other one. And then you need from 9 to A. In fact, it's probably 0 to 2, 2 to 9, 9 to A. Okay. And so it's probably something like this. That's the 0 to 2 move. This would be about the 2 to 9 move. And then this is like the 9 to A move. And so you just need to find out what that optimal highest ordered sequence is to get it to do what you want. To go from 9 to 8 would be something like this. To go from 8 to 0 like this. So you're not getting, like, you notice that 9 to A here, somewhere in here you start seeing right here at that line, it's the same sequence here. 4 to 5, 5 to 6, 6 to A. Now, unfortunately, this doesn't help because if you look at the problem itself, well, we do have a 9 to A, so we have that one already solved. Do we have a 0 to 2? Nope. Do we have a 2 to 9? Nope. Do we have a 9 to A? Do we have a 9 to 8? Yes, we do. Do we have an 8 to a 0? No, we don't. Do we have a 0 to A? Yes, we do. 1 to 7? Nope. 7 to 9? Nope. 9 to A, again, we have that one. 4 to 5. Nope. 5 to 6. Nope. 6 to A. Nope. So we're completely screwed on that one. 3 to 7. Nope. 7 to 9. Nope. 9 to A. Again, we have that one. So I think it's actually potentially not that bad. Unfortunately, we have some in here that we don't have in here, and we have some in here that we don't have in here. And again, looking at this, we would need to say for A, we need 1, 2, 3, 4, 5, 6, 7, 8, 9. Because we already know 0, A to 9. Or 9 to A, we know that path. But we don't know A to 9. So that's actually like when you see a 9 here, this is actually an A to 9. And so we've actually got this one and this one as well. We've got those solved. I think. Yeah, it's this. And so you have to figure out these little chunks to say, but that's a lot. Like for this one, arguably you have 10. In this one you have 10. So you have 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120 optimal paths. But once you figure those out, then your table is full, and then it becomes simple. It's just a matter of figuring out what is the optimal way of doing it. Right. And so arguably all of these are saying, like, the first number is technically A to 3. This one is A to 9. This one is A to 3. And so on. And so you just need to say, I need, what is the path for a given start and end character? I just don't know, how do you figure out because 29A is part of a solution here as well. So we have 0, 9, 1, 4, 3. 0, 9, 1, 4, 3. So we already have all of the at least starting ones. We have some of the 9As we also have solutions for. But all the ones in the middle, I think we were pretty much missing out on. We do have a 9 to 8. We do have, I think, a couple of other ones in there. So we don't even need to figure out all of them. We just need to figure out what is the optimal path for those ones that we don't have. And so how do you do that correctly? You know what I mean? And so that you know that your chunk is actually the thing that you want to do. It's funny because if you look at these 9, 1, and 4 all start out the same, but then they start diverging in terms of what they do. So you need an A to 0, 0 to 2, 2 to 9, 9 to 8. So there's actually 4 in here because you need to travel to 0 first, then you need to travel to 2, and then you need to travel to 9, and then you need to travel to A. Traveling salesman problem. Person problem. What's the shortest path that you can do? Well, I want to answer for this right now. I really don't know. I really don't know. Like with the first keypad, there's a shortest sequence that gets you to say, move it over and move up and hit that. So if you're controlling that first robot, you could say, okay, you're currently on A, so move over, or you're currently on 5 and you need to get to 7. So go down, go over, and press, like if you're 5 and 7, if you're in 5 and 7, and I was on, I could just say, okay, move up, move to the left, and press A. Okay. But that's me controlling this keypad. I need something else that I have a keypad that's controlling a robot that's doing this keypad that's doing this. So what I would need to tell it to do to go from 5 to 7 is I would need to tell it to go No, I can't tell it to go up because it's currently looking at A. So I would need to say, well, you need to move over. So now you move over. Now I hit A, so you press this, and now you're at 8. But every time I tell something to press, that might not be on A, because now the robot is on this. Now I need to tell it to move to the left. So now I need to have it go down. So I tell it to go down. God, this is a mess. I have to think about this a little bit. I know we have a couple of the answers within what we were told here. This part, the complexity part, that's simple. Like you're saying, this is, I'm assuming, is 68 characters. And then the numeric part of the code, ignoring leading zeros. And so you would basically, all of these are just this. And I'm thinking just to be safe, you could parse it to be an int. And that'll just be an int, and then you just multiply those two together. So it's not, that part is not hard. Because then you sum all those together. Yeah. We got to know what's the best way to get, like, well, actually, if I wanted to get to 5 to 7, is the best way to do it either to go to 8 and then 7 or go to 4 and then 7? And I don't want to think too stupidly, but could you almost argue and say it's better to go this way up and over? Would that actually work out to be better? I don't think so. But my point of why I'm bringing this up is to say, if I wanted to get from 6 to 7, do the pieces for going from 6 to 5, 6 to 9, and then 5 to 8, 9 to 8, and then 8 to 7, is that, which one is the less costly one? Or if I want to get from 6 to 5, 5 to 4, 4 to 7. You know, there's basically what I would consider to be reasonable paths. From 6 to 7, you would either go 9, 8, 7 over, you go 5, 4, 7 over, or you would go 5, 8, 7 over. All of those have the same exact number of nodes. Like if I was just thinking of the first robot, it's 1, 2, 3, 1, 2, 3, 1, 2, 3. They all have 3. If I want to get from 7 to 3, it's 1, 2, 3, 4. It could also be 1, 2, 3, 4. 1, 2, 3, 4. The shortest one is 4, but there's multiple ways of doing it. And so I think what you really want to do is say, find the shortest path for 7 to 8. Find the shortest path from 7 to 4. And then find the shortest path from 4 to 5. And find the shortest path from 8 to 5. And that may be different than the shortest path from 5 to 8. Okay. But once you have all of the paths, then you can just visually, you can just look. I don't even think you need a program for this. You can just look and say, well, if I was at 6 and I needed to get to 8, is it the combination of 6, 5, 5, 8, or is it the combination of 6, 9, 9, 8 that makes that better? And I'm almost thinking you really don't, I don't think you'd ever want to do like one of these where you kind of go around. That would actually be faster. I could be wrong. I could be wrong. But I think it's these singular ones that you just need to figure out. And so if you look at something like 1 to 7, that doesn't necessarily have, you have to go 8 to 1, right? And that actually tells you the fastest path here to get from A to 1. But ironically, it's also sort of telling you the quickest path to get from A to 0, A to 2, A to 1, or A3, 2 to 1. Because there's sub paths in between that. Now they're not actually they're not actually here, because you're not necessarily pressing the numbers between. In fact, you're not pressing the numbers in between here, but you are trying to find the fastest way to get to 1. And so to get from the fastest from A to 1 also tells you what would have been the fastest way to get from either A3, A0, or 3, 2, and then 0, 2. And then it would also tell you the fastest way to get from 2 to 1. Not sort of, because that last robot and what it's telling the middle ones, it may be hitting A, but it's because it's telling this next robot to push down, and they may be pushing down on an arrow key, and so it doesn't mean that it's giving you the shortest path in any way, shape, or form, because to actually get from A to 3 may not look like what you see in here in any way, shape, or form, because it has to get this robot and this robot to get this robot to get it to be over 1, and then it can press A on all those. And so that might be a different sequence. Yeah, I know you can't move over the bad hole. I get that. Although that day 21 beat me up. It was the last day in 2024 I saw the problem night of. And then did 20... Yeah, so maybe I also skip over this one too. I'm running out of time. Not really. But I don't want to spend too much time on this. Let's look at 22. I do have some feeling for at least the solutions that it's giving you give you at least some insight on it. But yeah, and no hints. Again, I'm going to be adamant, no hints on that. Yeah, if I need a hint, I will be explicit to say I would like a hint, but I am not doing that just yet. Okay, let's pause this and see if we can make some progress on this. As you're all teleported deep into the jungle, a monkey steals the historian's device. You'll need to get it back while the historians are looking for the chief. The monkey that stole the device seems willing to trade it, but only in exchange for an absurd number of bananas, of course. Your only option is to buy bananas on the monkey exchange market, the MEM. You aren't sure how the monkey exchange market works, but one of the historians senses trouble and comes over to help. Apparently, they've been studying these monkeys for a while and have deciphered their secrets. Today, the market is full of monkeys buying good hiding spots. Fortunately, because of the time you recently spent in this jungle, you know lots of good hiding spots you can sell. If you sell enough hiding spots, you should be able to get enough bananas to buy the device back. On the market, the buyers seem to use random prices, but their prices are actually only pseudo-random. If you know the secret of how they pick their prices, you can wait for the perfect time to sell. The part about secrets is literal, the historian explains. Each buyer produces a pseudo-random sequence of secret numbers where each secret is derived from the previous. In particular, each buyer's secret number evolves into the next secret number in the sequence via the following process. And by the way, that's why the random generator in C#, and this is true of other languages, they're pseudo-random, because if you generate enough numbers, it's going to come back basically modulo, you know what I mean? And then repeat it again. And that's why you sometimes put in a seed, because you want the seed to be different, but at some point it's going to repeat. And so to make something that's cryptographically, a random number generator that's cryptographically secure is harder. There are good algorithms for pseudo-random generation that are quick, but if you really want something that is considered, and again, what is truly random is almost a philosophical question at some point. But yeah, I'm gonna skip philosophy for right now. So calculate the result of multiplying the secret number by 64. Then mix this result into the secret number. Finally, prune the secret number. Calculate the result of dividing the secret number by 32. Round the result down to the nearest integer. Then mix this result into the secret number. Finally, prune the secret number. Calculate the result of multiplying the secret number by 2048. Of course, all powers of 2. Then mix this result into the secret number. Finally, prune the result. Each step of the above process involves mixing and pruning, just like brownies. Well, you don't prune brownies, you just eat them. To mix a value into the secret number, calculate the bitwise XOR of the given value and the secret number. Then the secret number becomes a result of that operation. If the secret number is 42 and you were to mix 15 into the secret number would become 37. I don't believe you. Well, I mean, I'm not saying I don't believe you. I'm just saying 42 XOR 15, 37. Hey, it works. To prune the secret number, calculate the value of the secret number module. And that looks familiar. That looks like a If you divide it by 2. No. It feels like that's a power of 2 as well. Is it? Yeah, it is. At that point, I could realize it was because I could see it. Then the secret number becomes a result of that. The secret number is this, and you were to prune the secret number. After this process is complete, the buyer is left with the next secret number in the sequence. The buyer can repeat this process as many times as necessary to produce more secret numbers. So if a buyer had a secret number of 1, 2, 3, the buyer's next 10 secret numbers would be really? So if I understand this right, you're saying each buyer's secret into the next secret number. So if I had this, I multiply by 64, I bitwise OR oh, okay, so I take that and XOR it with this number, and then I get a new secret number. We divide it, and then we multiply it again. And so if we start at 1580, I think if I understand this right, it's saying this is your secret number. So first you multiply it by 64. You take that result, mix it into that, prune it. Now that's each buyer's secret number evolves into the next secret number in the sequence via the following process. This is written a little oddly. It sounds like you do this. Becomes the result of that operation. Then the secret number becomes the result of that operation. So you get a result, multiply it by that. You mix it, that becomes a secret number. Then you prune it, that becomes a secret number. That is now used in here, and then that's used in here. So I think you do all three of these to get from this to this, and then from this to this. Okay. Each buyer uses their own secret number when choosing their price, so it's important to be able to predict the sequence of secret numbers for each buyer. Fortunately, Fortunately, the historian's research has uncovered the initial secret number of each buyer. Your puzzle input, for example, these numbers. This list describes the initial secret number of 4 different secret hiding spot buyers on the Monkey Exchange Market. If you can simulate secret numbers from each buyer, you'll be able to predict all of their future prices. In a single day, buyers each have time to generate 2,000 new secret numbers. In this example, for each buyer, their initial secret number and the 2,000th new secret number would be these. Adding up the 2,000th new secret number would produce this. For each buyer, simulate the creation of 2,000 new secret numbers. What is the sum of the 2,000th secret number generated by each buyer? God, I do not want Copilot. Jeez. So you basically just say, here's a number. And does it ever repeat? I'm sure it does. I'm sure that there is a repeating some sequence thingy to this, but we're going to have fun and we're just going to do the first part. Because I don't think the first part should be too terrible. This is day 22. So we'll save day 22 input. And we'll close that out. And so what we're saying here is we got these 4 numbers. That would give these as the 2000th one. So we want to say something to say, how do we want to break this up so that we get some decent testing around this? I say, if I give you this number, then get me a new secret number after n iterations. So I could say after 1 iteration, after 2 iterations, after 3, you know, and then I could have this and this. So I can say, get me a secret after 2000 iterations. That should give this. Bye-bye. We're doing 22. Okay. Yes, we have completely skipped over that. This is day 22. Day 22. Let's clear this out. We'll keep our input here. Get rid of all that. Kill all this. Get rid of that. Okay. So for each number, we're gonna want to do this as a big integer just because reasons. So we get our input. Var secret numbers sum is equal to that, and we'll return that. Of course, there's going to be more to it than that. Now what we want to do is we want to say for each var item and input, we want to say var initial secret is equal to big integer parse of that item, culture info, current culture. Okay. And then we're going to have some function here, private static big integer get secret big integer initial value, and then we're going to have int iterations. Okay. And what we're going to do right now is always return big integer 1, which is stupid, but it at least gives us a signature that I can call it. So I'm going to say and we're going to make this public because I want to be able to call this independent of part 1. Okay. But for the problem part 1, we're going to get the initial sequence, and then we're going to say secret number search plus equals the initial. We're going to say solution day 22 get secret of our initial secret 2000, because we're supposed to do 2000 iterations. Yep. And so we'll get some number here, and we're going to return it. Now, if we put a test around this, as you do, so make that, and so we're going to want to say here is test, yes, public static void test case. Our initial secret is this. After 1 iteration, we should get this. Get secret. We're going to say these are longs because we can't put a big integer into an attribute. Boo. But we can't do that. So we're going to say long initial secret int iterations long expected secret. Okay. And so what we're going to say here is now assert that solution date 22 get secret of our initial value, initial secret with iterations. Why are you barking at that? What did I enter it. Yeah, we don't need enter. We need iterations there. Is equal to the expected secret. Except we need that as a new big integer. There. Simple. And so if we run this, we'll obviously get the right answer. Which of course we won't. Because we're just returning 1 every time. But at least it did it right. So how many cases do we have? 1, 2, 3, 4, 6, 7, 8, 9. We got 9 cases. Wait, 1, 2, 3, 4, 6, 7, 8, 9. Yeah, 9 altogether. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 2, 3, 4, 5, 6, 7, 8, and 9. So after 2, we should get this. After 3, we should get that. After 4, we should get this. 5 should give that. I really don't know if we have to worry about this exploding, but I'm going to just keep it a big integer for now. There. Okay, so that's our test cases. So now what we need to do here is say var new secret is equal to big integer 0, return new secret. Well, actually, we could say is our initial value. And then we're going to say for our I is equal to 0, I is less than iterations, I plus plus. Okay. So the first thing we're going to do, there's going to be part 1, part 2, and part 3. The first one we're going to do is say var part 1 result is equal to our new secret times 24. 64. Sorry, 64. Yeah, I was like, that's not a power 2, and I just said that. Okay. And then to mix, we want to bitwise OR that. So we want to say, take this and bitwise XOR the new secret. Okay. And then we prune it. And so that would be this whole thing module this number. And that's the part 1 result. That gives us what this does here. Right? Part 2 is we want to take part 1 divide it by 32, and I'm going to assume this rounds down because I think it does. And then we do this and this, and that gives us part 2 result. Okay. Now part 3 says we're going to take part 2 and multiply it by that. And that gives us part 3. And we're going to take part 3 and say new secret is equal to part 3. Does it actually work? No, not even close. Let's just do 1 for now. And do this step by step. Okay. So our initial secret is that value. Okay, that's going to be the new secret. So we step through. Now this should be, if I copy that value, let's actually go into calc here. And we're going to say it's that number times 64, which is equal to that. Okay. Now we want to XOR it with the original number that I gave, which is that. And then we want to do mod this number, which gives us this. So that's what part 1 should be. 254. Okay, that looks right. Okay. Now we're going to take this number and we're going to divide it by 32. And then we're going to XOR it with this. And then we're going to mod it with that. So part 2 should be this. And it isn't. It's not even close. Oh, I know. I just realized what I was doing wrong. This should be part 1, part 1. This should be part 2, part 2. Yep. Yep. Yop. What's that thing from the Muppets? The big yop. Look from the face. Okay, so I think we now got the generator working correctly. Yeah. I'm sure there's some little optimization I could do here. But I'm going to kind of just leave this for now, because it's literally doing what the problem says. And so now what we can do is we can come back here and we'll say that our initial sequence is the parse of the number. We then take the sum and we add it to whatever the next sequence would be after 2000. Now, if we had an input on a test, we just grab one of these. Because we want to do part 1, except we got to mark it as a test, and we're not going to be doing it as a test case. Nope. Take that off. So our input Oh, this is our input. Okay, got it. Sorry. There we go. And so we're going to do 22. And this should be equal to that. And it is. We skipped over 21. 22. So we're just going to go right to there. We'll scaffold 21 just because 21, but we don't have any code for it just yet. And it's going to say, make that expression body member because somebody, me, likes that as my coding style. So I'm going to say that, 22, 22. What does this give? The value could not, oh, I keep doing that. This number, is that correct? It's the right answer. Yay. Much rejoicing. And this is N22. Okay, that one really wasn't that hard. I don't want to be cocky. Don't get cocky, kid. But that one didn't feel like that was going to be too difficult to do. But let's see, after you have to do like 5 trillion iterations, what do you get? My feeling is that this is pseudo-random, and because it's pseudo-random, that means it's circular. And so you just need to, you would need to, and I'm not even looking at the second part yet. I'm just assuming that's what that's what it's about to do, but we're going to see in a moment if I'm right or not. If that's true, then you just need to find out what the sequence is until it repeats itself. And how long of an iteration do you need to do that? And so then you could say if it's 5 trillion, well, it's really 5 trillion divided by that length, and then it's just the rest of that to calculate the number. That's my guess. Let's see if I'm right. Of course, the secret numbers aren't the prices each buyer is offering. That would be ridiculous. Instead, the prices the buyer offers are just the ones digit of each of their secret numbers. So if a buyer starts with a secret number of 123, that buyer's first 10 prices would be just the ones digit of, okay, sorry. It took me a second to realize what it was saying. So 0, 6, the last one would be 5. This price is the number of bananas that buyer is offering in exchange for your information about a new hiding spot. However, you still don't speak monkey, ook ook, so you can't, there's a language called ook, but anyway, it's an esoteric programming language. So you can't negotiate with the buyers directly. The historian speaks a little, but not enough to negotiate. Instead, he can ask another monkey to negotiate on your behalf. Unfortunately, the monkey only knows how to decide when to sell by looking at the changes in price. Excuse me. Specifically, the monkey will only look for a specific sequence of 4 consecutive changes in price, then immediately sell when it sees that sequence. So if a buyer starts with the secret number of 123, that buyer's first 10 secret numbers, prices, and the associated changes would be, so you have this one, that generates this. So you go 3, so you go -3. But it's not, it's just the difference from this to this. So this goes up to 6, that goes down, that goes down. That stays flat, that goes up, that goes down, that stays flat, that goes down. Note that the first price has no associated change because there was no previous price to compare with. Right. Yes. So that's what you start with. You get the price, and then you'd have to iterate, get the change. In this short example, within just these first few prices, the highest price would be 6. So it would be nice to give the monkey instructions that would make it sell at that time. The first 6 occurs only after 2 changes. So there's no way to instruct the monkey to sell them. But the second 6 occurs after the changes 1102, -1, -102. So if you gave the monkey that sequence of changes, it would wait until the first time it sees that sequence and then immediately sell your hiding spot information at the current price, winning you 6 bananas. Each buyer only wants to buy 1 hiding spot. So after the hiding spot is sold, the monkey will move on to the next buyer. If the monkey never hears that sequence of price changes from a buyer, the monkey will never sell and will instead just move on to the next buyer. Worse, you can only give the monkey a single sequence of 4 price changes to look for. You can't change the sequence between buyers. Okay, I'm a little confused by all this. You're going to need as many bananas as possible, so you'll need to determine which sequence of 4 price changes will cause the monkey to get you the most bananas overall. Each buyer is going to generate 2,000 secret numbers after the initial secret number. So for each buyer, you'll have 2,000 price changes in which your sequence can occur. Suppose the initial secret number of each buyer is 1, 2, 3, 20, 24. There are many sequences of 4 price changes you could tell the monkey, but for those 4 buyers, the sequence that will get you the most bananas is -2, 1, 1, 3. Using that sequence, the monkey will make the following sales. For the buyer with the initial secret number of 1, changes 2, 1, 3 first occur when the price is 7. For the buyer with the initial sequence of 2, it doesn't occur in any of them. So by asking the monkey to sell the first time each buyer's prices go down 2, then up 1, then down 1, then up 3, you would get 23 bananas. Figure out the best sequence to tell the monkey so that by looking for that same sequence of changes in every buyer's future prices, you can get the most bananas in total. Are you crazy? Are you daft? So it's saying here that this would be after 2,000 sequences or iterations. This would give you the most. And it's just saying for the first one, this occurs when the price is at 7. And and the price again is the ones digit. But I mean, there could be other 9s in there. It's just saying those changes first occur when the price is 9. So by asking the monkey to sell the first time each buyer's prices go down that sequence, you get that many bananas. And that's saying for those 4 numbers, that's the best. That's the most amount of bananas you could get. This is bananas. No pun intended. Because the input is very big. Okay. And each number would give 2,000 prices. And each one of those has its own set of sequences. So yeah, this one becomes really hard. And again, there's an optimization here. I'm sure I just need to muddle over this for a while. And with the pseudo random number generation of it, that eventually you'll repeat yourself. And when you repeat yourself, you're going to give the same exact number. And I don't think it's necessarily that it repeats every, if I go back to the solution here, 16.7 million numbers. It could, but I don't know if that's actually true or not. Like, even if you came back to that number, well, no, it would have to. Because if you ran, like, if this produced a 5, and as it's going through, the maximum number of repeated numbers could be this. It's gonna repeat after this this many iterations. It has to, or less. But there's obviously 16.7 million different numbers you can put in, but all of them are going to repeat after that number, because all of them are getting module that number. And so no matter how big of a number you put in, it will get module down that number, and then after that point you're bounded by that size. And so eventually it's going to repeat this. Okay. Of course, that doesn't... If I come back to the problem here, what you're trying to do is for all of those numbers is you want to find a sequence within those 2000s of... You want to find a sequence that gives you the best price for all of those initial inputs. And you'll notice that in this one, it has a sequence, but it doesn't have this sequence within it. But still, overall, that sequence is the best for all 4. And so you can't just go through like the first number and say all their sequences, does that exist? And then what is its cost? You know? You have to find a sequence that gives you the most amount of money, which in this case is bananas. And the whole problem is bananas. Ugh, excuse me. Just kind of curious. Do any of these numbers... any of them... are any of them bigger than this? It's hard to say, just by looking at it. No. I don't think so. I mean, just a cursory glance, I don't think any of them ever start at over that number. But you can't just say, like in the first one, find me all the ones that are 9s, because that may be good for this number, but the next one gives a completely different set, and especially even for 9s, it might not even exist in there. So yeah, I gotta think about this one too for a while. This is one of those that you could brute force, but the ability to brute force it would take forever to figure out. You'd eventually figure it out, but you'd have to look at all the different possibilities and combinations and just bleh, just gross. That would be awful, you know. If you think about it, you look at the first one, you say, here's a sequence. Okay. Well, for all the other numbers, what do their sequences look like? Like, what are their differences? And then for the next sequence, which is just shifted over one, we know exists in this one. What does that give for all the rest of them? So you have to do that 2,000 times. And you have to look at each one's numbers to say, where do you have this as your price the first time? Which isn't too bad, because you have to only do it for the first time, right? Well, you have to see where that change happens the first time. That sequence change. So it's not the first time the price is there, but the first time that sequence change is there. And so you'd have to find all the times where you have a sequence that starts with -2, and then for all those that has a sequence of -1. And then or 1, and then for those that have a -1, and then for those that have a 3, assuming that you actually even find that. And then if you do, what is the price? So again, I know I don't have the specifics in how I would store all that. You could do it. I mean, the number of lines, which is the amount of numbers here, is what? 1,500. So you'd have 1,500 numbers. Each of them would have I was about to say, could you get away with not even storing the price, but you need that? I mean, I guess you could say too, well, because you just need the first time a sequence occurs, but you have to do that for basically 1900 on the top first line, and then you have to do that again for that one. That just feels like that would take forever to do, and then you got to find which sequence gives you the most number of bananas. Right? What's the most bananas you can get? So you have to find a sequence of price changes that gives you the most bananas. You could, for all 16 million numbers, say, well, what would the... Even if you did that, though, I don't think that gives you any help. Because it gives you 16 million numbers. That could give you all the prices, and you could figure out all the price changes. You can just say... Yeah, I don't know. I'm going to stop here because I've been going for almost 2 hours. And I kind of see what this... I mean, I see what this is doing. I know what you need to do it, but there's got to be a trick to make this go fast, because if you don't, you could be spent in hell trying to get this to actually finish. So I'm gonna noodle on this one too, but at least we got one solved. At least we got something solved. So, we got that going for us. If we go back up to our calendar here, our stats, no, Yeah, we got 22. Would be nice to get to 40. And I think, yeah, I might do 23, 24, and 25, just like the first parts. And then come back 17. Man, that one just threw me for a loop. And these have also kind of thrown me off with their part 2s. But I'll think about it. I'll think off it offhand. Again, it's mid-January or even a little bit past that. And so I need to really put the brakes on this at some point very soon and start spending some time working on some stuff that I need to get done off camera. And I am also debating, do I do all of this? You know, or do I say, if I can't get this done by the end of February, then I just stop, you know, and that's where I ended up. But I really don't want to do that. But it's a time cost thing. And I want to get to streaming some other work that I have on some other projects and just spending time on that. So for now, I am going to stop with this problem and with AOC. I will potentially be doing a stream on this. In fact, tomorrow I'm going to do a lot of streaming. So I am planning on at least doing one more coding stream. And if that means I just keep it to the simple first parts, hopefully these are simple. What are the stats on those days? Not too bad. Not too bad. So I might do that too, and just get the part 1s, see if I can get the part 1s done on these days, and then I'll just determine where I go from there. But I am planning on doing a Splinter Cell stream tonight after dinner, and I'll be doing more of that tomorrow as well. So if that interests you, you can check that out then. In any event, I'm done for now, so thank you for watching. If you haven't subscribed yet, please subscribe. I would greatly appreciate that. And with that, I am done with the stream. Thank you all for watching. Take care, and I hope to see you in the future.